Welcome back, everybody, as we continue section 14.6 on tangent planes and differentials. The next thing I want to talk about is something called an increment. This is going to lead into our next topic dealing with linear approximations. So an increment is actually the exact change in a function. So let's say that we have a function of two variables, as we've been dealing with, f of x, y, and we make small changes to a point in the x and y direction. So let's say we're at a fixed point, x, y, and we change the x coordinate a little bit, we change the y coordinate a little bit, and we call those changes delta x and delta y. Then the increment delta z is the exact change in the function value, in the z value. So that's the function value at our new point, x plus delta x, y plus delta y, minus the function value, the original function value, f of x, y. And that gives us the exact change in our function. Now that leads to the idea of a differential, where we're going to change the notation slightly, and we're still going to have small changes in x and y, but instead of calling them delta x and delta y, we're going to call them dx and dy. But we're still going to think of these as small changes in x and y. And we're still going to deal with a function of two variables, and we define the differential, sometimes called the total differential, as dz, this is the differential itself, equals the partial derivative with respect to x at xy times dx, plus the partial derivative with respect to y at xy times dy. Or you can write it with this other notation, partial z with respect to x dx plus partial z with respect to y dy. Now written in this way, this might remind you of the chain rule and how we wrote the chain rule when x and y were functions of one variable. So let's say x and y are both functions of t. This looks pretty similar, except we don't have these as derivatives with respect to t. So what's the difference? The difference is when we were using the chain rule, we wanted to think of z as a function of one variable, a function of t, and see how that get the derivative with respect to z, with respect to t, when in fact z was written as a function of two variables, x and y. What we're doing here is slightly different, right? It's a different idea. It is that we have some function, we're changing the function in the x and y directions a little bit, and we want to approximate how that changes the value in the function itself, how it changes the z value. Now this also has connections to the tangent plane. If you think of dx as x minus x naught, dy as y minus y naught, we could subtract that z naught over here and think of this as z minus z naught. This gives us the same equation as a tangent plane. And so all of these ideas are related. So what is this differential? This differential, whereas the increment was the exact change in our function, the function value at our new point minus the function value at our old point, this differential is the approximation of the change using the linearization, so using the tangent plane. So you see this idea is directly related to the ideas we talked about in the last video. So what I want to do now is give a picture of what's happening to give you an idea of the difference between these things. So in this picture, let's say we're starting at this point xy, and this black plane is just a horizontal plane, just represents no change. So this is completely flat. The z value everywhere in this plane is the same. Okay? And then what we're interested in is this red surface, this red kind of wiggly surface. This is f of xy. And we want to know, okay, if I start at this point and I end up at this point over here, what was the change in my function value? So if I use the increment, that exactly gives me this change. Right here it's a positive value because we went up, but it could be negative if the z value went down instead of up. Here are the sides of this wiggly surface, and this plane are the same. They're delta y or dy. We're going to use those interchangeably. And delta x or dx, we're going to use those interchangeably. So those give you the length and width of this horizontal plane and also where this slice of this surface is defined. So now, maybe I don't want to find the increment because this surface is described by a difficult function to deal with. If I wanted to calculate these things by hand, I don't want to deal with f. F is horrible. So instead, what I can do is I can use the linearization of f and use this blue tangent plane, right? They agree at this original point, but now I'm going to draw a tangent plane instead of the function itself. So this is the tangent plane. The function values are given by the linearization L of x, y. So now if I take this new point on the tangent plane, that's going to approximate this value minus this value is going to approximate the change in my function. It's not going to give me the exact correct change in my function, that's the increment, but it gives me the approximate change in my function, and that's the differential, that's dz. So that's what the differential tells us, is an approximation of how the function is changing. It's not the exact change. And it's approximation using the tangent plane, using the linearization. This idea extends to functions of as many variables as you want to be. So let's look at a function of 3 variables, and from here you can probably see how to extend that to as many variables as you want. So if I let w be a function of 3 variables, x, y, and z, it has to be differentiable in order to define the differential here. But first we define the increment. Delta w is f of x plus delta x, y plus delta y, z plus delta z, minus f of x, y, z. So you see it's the same idea before, but now we're adding these third coordinates. And the differential is defined as dw equals the partial derivative of w with respect to x dx, plus the partial derivative of w with respect to y dy, plus the partial derivative of w with respect to z dz. So again, same as before, but now we're adding this third term. So if you wanted to define this for as many variables as you want, you just keep adding coordinates here and adding terms here, and you get the same idea. So now let's do an example. First, if we're given this function of 2 variables, x squared plus 3xy minus y squared, let's just find the differential dz. So dx and dy are just going to be variables. We don't know what those are. In this context, all we need to do is find the partial derivatives here. So dz is the partial derivative of z with respect to x dx plus the partial derivative of z with respect to y dy. So I just need to calculate these 2 partial derivatives and I'm finished. So if I go up here, the partial derivative with respect to x, I get 2x plus 3y. That's what I have here. The partial derivative with respect to y, I get 3x minus 2y. And that's what I have here. And I'm finished. That's the differential. But that's not entirely interesting, so let's see how we can use the differential. So we see if x changes from 2 to 2.05 and y changes from 3 to 2.96, compare the values of delta z and dz. So compare the actual change in the function, this same function, and the approximate change in the function. Okay, so first let's deal with the differential. Since we already have a formula for the differential here, we need to figure out what dx and dy are, and that's going to be the change in x. So, and the change in y. And these are going to be the same. So we're going to use delta x and dx and delta y and dy interchangeably, just say they're the same thing. To figure out the change in x, I look at where x stopped minus where x started, 2.05 minus 2, and that's 0.05. That's the change in x. Same thing for the change in y. It stopped at 2.96, it started at 3, so the change in y is negative 0.04. So these are my dx, dy, or my delta x, delta y, both of them. So now I can go back to this formula. I know what dx is, I know what dy is. Now what do I use for x and y? For x and y, I use the original point. So again, here's my equation for the differential we found before. X and y are going to be the starting point, 2, 3. So I started at 2, 3, I moved to 2.05, 2.96. but I don't use those numbers anywhere. I use those numbers to come up with these dx dy values. So now I can just go ahead and plug everything in. So for x, I plug in 2, so there's 2 for x. For y, I plug in 3, so I put a 3 here, 3 there. For dx, I plug in 0.05. For dy, negative 0.04. And then I just work this out, right? So this is just 13 times 0.05. This ends up being 0. So I get that the differential is 0.65. Now moving on to the increment. This is going to involve a little bit more work, as you might imagine. The approximation is easier than the actual value. So let's see, scoot this up. So there's the definition of the increment. The function value at x plus delta x, y plus delta y, minus the function value at xy. Once again, xy is going to be 2, 3. X plus delta x, y plus delta y, that's where I end up. So x plus delta x is 2.05. You could actually do the math, but it's already given to us. This is our ending point. And y plus delta y is 2.96. So that's what I've written here. We're actually going to find f of 2.05, 2.96, and subtract f of 2, 3. This is the new function value minus the original function value. That's the exact change in the function. Okay, so let's do these two function values independently. Before I take this sheet away, let's just remind ourselves that our function was x squared plus 3xy minus y squared. And now let's get rid of that. Okay, so now I want to find f of 2.05, 2.96. So I'm going to have 2.05 squared plus 3 times the product of those two numbers minus 2.96 squared. Now we can do this by hand, and I did do this by hand. It's a little frustrating. Not frustrating, really, just annoying dealing with these decimals, but it can be done. Have to go back, I don't know what grade you learn multiplying decimals. But you'll have to go back there and remember these things. So 2.05 squared gives you 4.2025. This product, 3 times 2.05 times 2.96 is 18.204. And then 2.96 squared is 8.7616. So now I just add these two terms, subtract that term. I get 13.6449. So that's the value of my function at the ending point where everything's changed. Now if I go back and find the function value at my original point, that's much easier. It's just 13. So now all I need to do to find the increment is subtract them. So the actual change in my function was 0.6449. Now I've taken away what we got for the differential, but if I compare the two, the differential was 0.65. That was the approximate change. The actual change was 0.6449. So this is the difference here is about 5 thousandths, or 0.005. That's pretty small. They're pretty close to each other. And if you do this on your own on a piece of paper and you do everything by hand, you'll see that calculating this dz, this differential, is much easier than the increment. So that's really the advantage of using these approximations. Same idea with the linearization. You're approximating something with a simpler function rather than using a complicated function. And again, with the same idea with the linearization, these differentials are only good approximations if the dx and the dy, these changes, are small. You make these too large, this is no longer a good approximation. Okay, so let's summarize what we've done in this section so far.
In this section, we've talked about 3 different concepts, all involving a function of 2 variables at a fixed point x naught, y naught. The first idea was a tangent plane. So if we think of this function as a surface, we come up with a tangent plane, which is a plane tangent to this surface at the point x naught, y naught. And the equation for the tangent plane is given here. We've seen that a few times before. The second idea was a linearization. This is a function of 2 variables that's used to approximate this function at points close to x naught, y naught. And if you look at the equation for the linearization, it's exactly the same as the tangent plane. There's no difference here. The only difference is the context. Here, we're talking about a plane that we graph, And here we're talking about a function that we use to approximate f, as long as we keep x and y close to x naught, y naught. The third concept was a differential. Now this is a function of two different variables. The two variables here are dx and dy, and we think of these as small changes in x and y. And what this is used for is to approximate the change in your function value based on changes in x and y. And it uses a linearization or a tangent plane to make that approximation. So it's not the exact change in this function, it just approximates the change in the function. And if you think of this small change in x as x minus x naught, this small change in y as y minus y naught, and this small change in z as z minus f of x naught y naught, or z minus z naught, then you'll see that this is really the same equation as the other two, just a different context. Now here, we don't actually think of these as differences, right? This is just going to be some small number, and then we get our answer. So that's all I want to talk about in this video. In the next video, we'll finish up section 14.6 with a couple more examples on how to use the differential, and it'll be a shorter video, and then we'll move on to something else.